today we're going to start with a little bit of background about what a mole is in chemistry. It is basically, for chemists, a way to measure the number of particles, atoms, ions, formula units, or molecules that is large enough to see and handle. Remember, atoms are too small to be seen or measured, so chemists needed to come up with a way to be able to handle a standard unit of measurement in terms of chemistry. And they just assigned it based on carbon-12 isotope, which if you need more of that kind of background information, I can give it to you, because a lot of students seem to have a hard time connecting, well, mass and moles and atoms, but just trust me, they figured it all out and it works. But you can just define a mole as any number of things. Just like a dozen is 12 of something, well, one mole happens to be 6.022 times 10 to the 23 things. And those things are going to be called units. And the units are going to be things like particles, atoms, ions, formula units, and molecules. So the chemists said, well, we need a standard way to make measurements. We need a standard unit. Just like meter, liter, grams, seconds. This is the chemistry unit that we measure and relate everything back to, okay? And we call it Avogadro's number, or some people like to call it avocado number. So how do we know when we have a mole? Can we count it out? Can we weigh it? Yes, we can. And we weigh it by calling it molar mass or the atomic weight. So we'll revisit the idea of atomic weight or molar mass in another lesson later, but I'm inserting it in here and I'll come back to it later for you to remind you. But mass in grams numerically equal to the atomic weight of the element, which is also in AMUs. But again, based on carbon-12, they worked out that AMUs, or atomic mass units, are going to be equal to grams, which we call the molar mass or atomic weight. So a lot of times we use some words interchangeably. You can look at the periodic table and see that atomic weight and atomic mass are sometimes the two things that are used. And sometimes they do give the atomic weight or atomic mass in terms of AMUs. And in chemistry, we kind of use those things interchangeably. When we're referring to covalent compounds, we refer to it as molecular mass or molecular weight. And then in terms of ionic compounds, sometimes we use the words formula mass or formula weight, because ionic compounds are not molecules. All right, so an important thing to understand how we solve chemistry problems is through a process called dimensional analysis using conversion factors. And conversion factors is nothing but a ratio or a fraction of equivalent values that are used to express the same quantity, and they equal 1. And you already know these conversion factors and actually use them. You use them with your pay rate. If you get paid $9 an hour and you work 40 hours a week, how much money do you get? We use the same thing in terms of filling up our car for gas. We know that it's $2.50 a gallon and I can afford to pay 10 gallons, so you can figure out how much you can get for 10 gallons. We use time units, equivalent time units all the time, 60 seconds in a minute and 24 hours in a day. And we can write them as a fraction that is equal to 1. So we can say 60 seconds over 1 minute or 1 minute over 60. If I wanted to know how many seconds are in 20 minutes, I just simply need to multiply by 60. All right, so hydrogen has an atomic weight of 1.00794 grams. Therefore, based on this concept of the mole, then we can say that 1 mole of hydrogen has a mass of 1.00794 grams. We can also say, based on Avogadro's number, that 1 mole of hydrogen has 6.022 times 10 to the 23 hydrogen atoms in it. So we can write those values as conversion factors. We can say 1.01 grams per mole, or we can say 1 mole per 1.01 grams. Or we can say 6.022 times 10 to the 23rd atoms per 1 mole, or we can say 1 mole per 6.022 times 10 to the 23rd atoms. And this is true for all of the elements, and we can also write them just like this for compounds too. And we can use these to help us go from one thing to another, to another, to another. So, if magnesium has an atomic weight of 24.3050 grams, what are the 4 conversion factors that you could write? So, if you would take a moment and pause this video and try to write these 4 things down and then restart. 1 mole per 24.3 grams, or 24.3 grams per 1 mole. Or 1 mole per 6.022 times 10 to the 23 atoms, or 6.022 times 10 to the 23rd atoms per mole. So let's talk about what this actually would look like in terms of chemical compounds. Well, let's just look at things like elements, like sulfur. If you look on the periodic table, you will see that sulfur has a rough mass of 32.1 grams. So that is actually what, if I took a beaker, went into the balance, and kept adding sulfur until it equaled 32.1 grams, which is what's on the periodic table, that's equivalent to what 1 mole of that is. In this 32.1 grams, which is 1 mole, there are exactly 6.022 times 10 to the 23 atoms of sulfur in there. We just can't count individual atoms, and we can't measure mass of atoms. So they came up with this nice convenient unit to convert between things called the mole. And same thing applies to iron. If you look here for iron on the atomic weight on the periodic table, 55.9. That's equal to 1 mole, and that's also equal to 6.022 times 10 to the 23 atoms of iron. Now, let's look at sodium chloride. It has a formula mass of 58.5 grams when you add sodium plus chlorine, which is 22.9 plus 35 point something, 4, okay? So when you add those two together, you get 58.5 grams. In 1 formula unit, that is what that is. In 1 mole of that, you have that many formula units, 6.022 times 6.022 times 10 to the 23rd. So that many units of those. However, because it's a compound, we also have Avogadro's number of sodium atoms and Avogadro's number of chlorine atoms in that. Isn't that something? Same thing with potassium chromate over here. If we add the potassium, the chromium, and oxygen, we get this mass, which is 1 mole. We have 1 formula unit of here, which is equal to 1 mole, which would be Avogadro's number. But you also have 2 times Avogadro's, and 2 times Avogadro's, and 3 times Avogadro's for each of the elements. Same thing here with this compound, C17H22O something. I can't read that. It's not a very good picture, sorry. So, but carbon, hydrogen, and oxygen, this mass equals that. You also have that many molecules of Avogadro's number plus Avogadro's number times each subscript for each element present in that 1 mole. So you see how useful a mole is? It allows us to figure out and find so many different things. All right. So at this point, I'm going to stop the video on the examples, and you'll have to pick up on the video where I work the examples, but I want to take a moment and go to the internet and show you where in Schoology, under resources, I want to point out, oh, I never made a mole. I need to do this. So I'm going to include in resources, besides this chemistry formulas and equations, this mole map, and I'll point this out to you the next time. I did it on my home computer and forgot to add it here, but it's a really handy thing. Let me just find some for you, and I'll show you what I'm talking about. Well, one of them is on the CK12 that I had pulled up. I meant to show that to you. So let me go back to that. This was a a nice thing for you to look at that you can use. So, but I meant to make it as a PowerPoint that you could pull up and access anytime you wanted. I think it was here. Let's see. So one image that you want to refer to that's useful to you, I thought it was on this one. Maybe it's not on this one. Which one was it on? Let's see. I'm sorry, this isn't working out so well. Maybe it's on this picture. That's on one of these lessons I found, and I liked it. And I was going to make a PowerPoint to include the picture, but I'm not having any luck finding it because I know it's on here somewhere. Oh, here it is, the mole roadmap. Sorry. Okay, so I will include this picture. I'll make a little PowerPoint, and I have this one and a couple of other images because we're going to be going between moles and particles and moles just for today. But then we're going to add moles and mass and moles and mass. And then at some point when we cover gases, we'll revisit the idea of moles, and then we'll learn about how to do it with gases. This picture is very useful because it gives you this guide here, how to go from a particle to a mole. You use this conversion factor. And then you just flip the conversion factor when you're going from moles to particles. But as we get into chemical equations, this now gets doubled because we have to convert between two different substances. So I'll make sure I make that little presentation so that you have little slides that you can look at to help you reference how to solve problems, okay? I thought I had put it up there and I hadn't. It's on my home computer. I apologize. But this is very useful to you, for you to use, and you'll want to reference back to this, okay? I don't know if I'll assign this particular lesson or not yet. I haven't gotten that far in my decision-making process. Okie dokie, artichokes. All right.